Alright, we left off talking about this precipitation reaction between silver nitrate and sodium chloride. And so we had our sodium and nitrate spectator ions floating around in the water, while the silver and chloride ions had formed the precipitate that has sank to the bottom of the container. So this is what this reaction looks like, written out how you're used to doing it. We're showing that the silver nitrate is soluble, so is the silver chloride, and is the resulting sodium nitrate. However, the silver chloride is a precipitate here. Now, this isn't really that accurate of a depiction of what's happening. The more accurate way of writing it, while more tedious and time-consuming, is the complete ionic equation. Here we show everything that's aqueous, everything that's soluble, busted up into ions, how it really is in water. So we've got the silver and the nitrate floating around aqueous, as well as the sodium and the chloride. And then, once mixed, the sodium and the nitrate continue to float around aqueous, while the silver chloride forms an insoluble precipitate, so we keep it together in the complete ionic equation. So basically, in a complete ionic equation, you bust up all the soluble stuff into ions. Remember to keep the polyatomic ions together. And you write the precipitate, the insoluble product, together as one molecule and label it solid. Alright, so once again on a molecular level, we've got the ions floating around in the solution until the silver and the chloride come together and make the precipitate. That's actually where the reaction's happening. The sodium and the nitrate are spectators. They're not doing anything. They're not actually reacting in this situation. Alright, so they just continue to float around aqueous. Now, they're spectator ions. So, really, all that happened here was this. The silver and the chloride combined and made a precipitate. Ta-da! So, another way to represent this reaction that is a lot faster than the complete ionic equation is the net ionic equation. In the net ionic equation, you only show the species that actually reacted, that actually underwent some kind of change. In this case, it was the silver and the chlorine that went from being aqueous and soluble to forming the silver chloride precipitate. So the net ionic equation would involve just including those species there, and you would simply just X out the spectator ions, the sodium and the nitrate. You don't even bother to write them because they didn't do anything. They didn't change at all. They didn't participate in the reaction. So the net ionic equation is simply, if I can get it to pop up, this. The silver ion plus the chlorine ion made silver chloride. That's it. That is the net ionic equation. So for a precipitation reaction, the net ionic equation is just the ions that form the precipitate. That's all you show. Alright, so precipitation reactions, as we said, they come in different varieties. You can get pretty colored precipitates. A precipitation reaction just occurs when you mix two aqueous solutions that were made by dissolving ionic compounds in water. And if a reaction occurs, a precipitate, a solid, is formed. It can be white, black, green, there's pink ones, and your pretty colored ones tend to be transition metals. They tend to form colored crystals and colored solutions as well. So here's another example. This is silver nitrate. Alright, in this example, we have silver nitrate. Here it is, what it looks like in real life. And then on a molecular level, we've got our little silvers and our nitrates floating around. And then sodium chromate. Chromate compounds, that chromium makes a lot of cool colors. In this case, it's a yellow solution with the sodium and the chromate. The sodium chromate is soluble because it has sodium in it, and the silver nitrate is soluble because it's got nitrate in it. But when we mix them together, the sodium and the nitrate continue just to float around in the solution, being spectators, but the silver and the chromate make a solid, a precipitate. And you end up with this orange solid at the bottom. All right, so solubility rules, again, posted, kind of presented in a slightly different way. So soluble compounds include anything with an alkali metal, a group 1 metal, or ammonium, any nitrate, any hydrogen carbonate, any chlorate, any Cl, Br, or I compound, and any sulfate. Those are soluble, but there's some exceptions. For the halogens, silver, mercury, and lead are insoluble, and for sulfate, we've got calcium, strontium, and barium, the bottom of group 2, are insoluble, as well as silver, mercury, and lead again. So the sulfate exceptions are basically the same as the halogens, plus the bottom of group 2. All right, now the insoluble compounds are carbonate, phosphate, chromate, and sulfide. Those tend to be insoluble. The exceptions being, unless they're with a group 1 metal, then that rule trumps all other rules. If there's a group 1 metal, it's soluble. Then we got the hydroxides. Those tend to be insoluble unless it is with a group 1 metal or barium. Now, if you remember the previous solubility rules, there's a mosquito, I'm sorry. If you remember the previous solubility rules, there was more exceptions to the hydroxide rule. This is frustrating, but depending on which book you look at, the solubility rules vary a tad. In a high school level book, they tend to be a little bit more simplified, and then in your college level books, there'll be more exceptions. I will make sure to give you the right list of rules that you need to know for the AP exam. All right, so predicting the products of a precipitation reaction is pretty simple. You just swap the metals. Your ionic compounds are strong electrolytes, as you know, and so in order to predict the products, you've got to get the charge on all the ions in the reactants, so that way you can figure out how they are going to combine as products. You need to know the charges of the reactants so that you can determine the subscripts for the products and write their formulas correctly. So using those ion charges, predict the formula of the products. You just simply take the positive ion from one reactant and put it with the negative ion of the other reactant. And then you do the crisscross method. However, I'm not sure how Mr. Sheldon worded it, but however you learned to write ionic formulas in the past. Then, of course, you have to balance the equation. Get the formulas correct first using charges, then insert coefficients to balance it. Now, you just got to figure out which of the products is going to be solid and which one's going to be aqueous using your solubility rules, of course. Then, if you're wanting to write the net ionic equation, figure out who your spectators are. Which ions were aqueous on the left side and continued to be aqueous on the product side, on the right side. Those didn't react, those didn't do anything, so they're spectators. So write the net ionic equation only showing the ions that were involved with forming the precipitate. You can ignore the others. So it's helpful to pay attention to exactly what species are present in the reaction mixture, who was solid, liquid, gas, or aqueous. Right now we're focusing on precipitation reactions, but we will be constructing net ionic equations for other types of reactions as well. And in that case, we're not just looking for substances that turned from aqueous to solid, but we're also looking for substances whose charges changed, or who went from solid to liquid, or gas to solid, or gas to liquid, etc. So the substances that changed in some way are included in the net ionic equation. If to really understand reactivity, we have to be aware of what exactly is going on and changing in the course of a reaction. Alright, so the molecular equation, when I say molecular equation, I mean just the traditional way you are used to writing balanced equations, okay, like so. Complete ionic equations are the kind of tedious ones. You only break apart your strong electrolytes, so that would be your soluble ionic salts, your strong bases, and your strong acids. You bust those up into ions, but you leave the insoluble precipitate, of course. And anything that isn't ionic, we haven't had that yet, but we will. Any molecular compounds like carbon dioxide, you would leave those together in the complete ionic equation. That is really a more accurate depiction of what's in the reaction mixture. It just takes a little bit longer to write. Alright, for the net ionic equation, you cross out anything that does not change from the left side to the right side. If its state stays the same and charge stays the same, nothing about it changes, then it's a spectator ion and you can cancel it out. In the net ionic equation, then, you'll just be kind of catching and showing the ions that actually did something. In this case, in this example, it was the silver, and the chlorine went from aqueous to solid. The things that didn't change, remember, we delete those from the net ionic equation and we call them spectator ions. So, to do this, first we have to have a balanced molecular equation. Do not forget to balance them. Okay. Then you break apart all your strong electrolytes to construct the complete ionic equation. Cross out anything that remains unchanged. Okay, and then write the net ionic equation with the species that remain. Alright, so another example of another precipitation reaction. Here we have lead nitrate. It's soluble in water because all nitrates are soluble. Then we have sodium iodide. It's soluble in water because anything with group 1 in it is soluble. The metals switch places. Now notice we have 2 nitrates over here. And when we go to write the products, we're not just going to put parentheses 2 around our nitrates, because that's not what happens. The nitrate combines with the sodium. Well, sodium's +1 and nitrate's -1. So that's the correct formula. We'll worry about the fact that there's more nitrates on the left after we've written the formulas. We'll go back and put in the correct coefficients to balance it. Okay, so don't worry about how many what's are on each side until you've got all the formulas written. So the sodium will combine with the nitrate, and then the lead will combine with the iodine. Well, lead can be +2 or +4, so how do you know what he's doing right here? Well, you have to look at who he's hanging out with. He's hanging out with 2 nitrates. Nitrates are -1, and so if this lead is making a neutral compound with 2 negatives there, well, he must be 2 positive. And for a precipitation reaction, we want to make sure to keep him 2 positive. So when the lead combines with the iodine, we're going to make it PbI2 because the lead's 2+ and the iodine's 1-. Now we'll worry about sticking 2's in front of everything in order to make it balanced. Alright, the lead iodine is not soluble. Cl, Br, and I are soluble compounds, except when they're with silver, mercury, and lead. Alright, so that was our molecular equation. Now down here, we've busted up the strong electrolytes, except for the insoluble product. So that's our complete ionic equation. Now for the net equation, we'll just simply get rid of the spectators. That slash is not where it should be. It should be over the nitrate. So the sodium and the nitrate should be slashed out over here. And the final net ionic equation is my 2 lead ions, my 2 iodine ions, and then the lead-2 iodide precipitate. Notice I keep the net ionic equation balanced. Okay, you need to make sure that if there was 2 iodines in the original equation, that you have it in the final equation. Now, notice the 2's in front of the sodium iodide. Okay. And so it looks a little weird because now it's just in front of the iodine, but you have to distribute those coefficients when you write out the complete ionic equation. You have 2 sodium ions and two iodine ions. Make sure that everything's balanced, okay? And also, I've said this several times already, but don't break up your polyatomic ions. We just need to write it like this. Keep NO3 together. Keep the nitrate together. Alright, also don't get kind of lazy about it and not write the charges. It's an ionic equation, so your ions need to have their charge shown. You don't show a charge when they're all together in a compound, though, because the whole compound's a neutral. There's two pluses and two minuses here, so the charges cancel. So show your compounds as neutral. All right, there we have it. And once again, lead made a yellow precipitate. This happens a lot. All right, so here are some sample problems that we will do in class.